Hi there, this is homework 10. In the first question, we need to know Poisson process. This process is actually the one of the most basic process we need to know. And for this one, for Poisson process, we need to know that the x at t equals to 0 is 0, and we if we use the if we use the xt as the number, we use xt1 minus xt2 as the number of calls received in the interval of t2 and t1. So we should know the probability between this interval the number of calls between this interval equals to k is like e to the minus lambda t1 minus t2 and times lambda times t1 minus t2 to the k and over k factor. And we use tau to know the time interval, so we can rewrite the formula above to this formula, and we know that the xt is a Poisson variable, so their difference should also be a Poisson variable with the difference of two random variable is a Poisson variable with the parameter lambda times t, and there's another feature that if the intervals, this is actually one of the assumptions we made, if the interval t1 and from t1 to t2 and the interval t3 and t4 are not overlapping, so then we assume the number of calls in the two interval are independent. In the textbook, this assumption got proved, and for Poisson process, the expected value is a lambda t, and the autocorrelation is lambda square times t1 and t2 plus lambda, the mean of the minimum of t1 and t2. This value is actually the covariance of this process is a lambda times the minimum of the t1 and t2. So for the next process is a Poisson increment process, in xt. Xt is a Poisson process, so we have if yt, random variable yt, equals to xt plus epsilon minus xt over epsilon, then we define yt as a Poisson increment process. So in this process, the probability of a yt equals to n divide epsilon. So n is the number of call interval between t and t plus epsilon. So this probability equals to the probability of xt plus epsilon minus xt equals to n, and we know that this one is equal to this one is actually the Poisson process. So we use this formula in here, and so we have e to the lambda epsilon times lambda epsilon to n and over n factor, and we know the expected value is excuse me. So expected value of this process, if we divide epsilon is lambda. So the autocorrelation is lambda square when the interval is more than or equal to epsilon, and equals to this term if the interval is less than the epsilon. And covariance is 0, and lambda over epsilon minus lambda times t1 minus t2, which is tau, over epsilon squared. So the next one is point impulse process. So this one is actually the derivative version of Poisson process, and so it's like a limit when epsilon goes to 0 version of Poisson increment process. So this one, the expected value is lambda, as we know in the last process, its expected value is lambda too. So when epsilon goes to 0, this one keeps lambda, and the autocorrelation is lambda times the delta function of t1 minus t2 plus lambda squared, and the autocovariance is lambda times the delta t1 minus t2. The next one is a semi-random telegraph signal. For this one, we know that this is the probability of a number occurs in time interval t is actually from 0 to t. So the number is equal to k. The probability of it is e to the lambda t minus lambda t, and on this term, and so we have this like definition here. The xt is equal to 1 when this number is even, and xt is equal to -1 when this k is odd, and so we have the density function is probability of 1 is for this for the computation of this process, we can actually use Taylor series. It's actually the e to the lambda t. I remember it's a e to the lambda t. We rewrite it to its series form. Then we have two series, and we can make a sum. We can make a sum or make a difference, and then we have this this term is some version of this term, and so it's we know that the k is odd or even. So we have finally we got this density function, and then we can we can do the expect value. The expect value is e to the minus 2 lambda t, and the autocorrelation is e to the minus 2 times lambda, the absolute value of the t1 minus t2, and the autocovariance is e to the minus 2 lambda, the absolute value t1 minus t2, and minus the e to the minus 2 times lambda times t1 plus t2. And the next one is a random telegraph signal. So these two signal, this one is a semi-random telegraph signal. So because this for semi-random, because we know that x at t equals to 0 it start from 1, so it's not actually the true random. And for this one we plus we times a random variable a out here. So we plus a random variable, and its density function is it's 0.0, it's 0.5, and so it have two outcome. One is a equals to 1, and another is equals to minus 1. So for this one, we computed the density function. The first one is when y is equal to y is 1, and we have two circumstances. The first one is both a and x equals to 1, and another both of them are equal to minus 1. So we know the final probability is 1 over 2. And similarly, we have the probability of y equals to minus 1 is also 0.5, and the expected value is 0, and the correlation is e to the 2 lambda times the absolute value of the t1 minus t2, and the autocovariance is e to the 2 lambda times is also the autocorrelation, same value. And the next one is a random walk process. So for this one, we use the k equals denote the like in a fair dice trial, we use k for the number of heads show up, and n minus k as so n is the total number of a trial, and n minus k hence is the tail shows up. So and we use s. Actually we usually use 1 and minus 1 to denote head and tail. This time we use s and minus s, so it's a random variable. So for this one, if we use r denote the heads show up in n toss, so it's x equal to rs. The probability of it is this one is actually by the it's like the Bernoulli trial, and the final, this is the final probability. In the expected value is 0, and the autocovariance and autocorrelation is both the mean minimum of in n times s squared. So the last one, the last one is a Wiener process, and this one is like the limited version of a random walk. This one is when s goes to 0 and t goes to 0 and n goes to infinity, and so we use so we know the density function, and FWT is like it's like the Gaussian, it's like Gaussian distribution, the formula of a Gaussian variable, and so it's this equation here, and the expected value of W is 0, because still for a random walk is 0, and the autocovariance and autocorrelation is both alpha times the mean of the minimum of T1 and T2.